Everyone, we are back, and last time we went through examining what do stress strain curves look like for a simple uniaxial tension test, but we kind of skipped over a couple things. First, we didn't even talk about really shear much at all, but and we only really focused. We defined stress as force over area, strain is equal to LF. Oops, let me fix that. LF minus L naught over L naught. This glosses over something very, very, very important. We are typically going to be working with complex stress states, and the true definition of stress is a second-rank tensor property. So it has a direction and has a magnitude, but our stress is going to have two components. So stress is a second-rank tensor property, and we're going to see that happen right now. You've seen first-rank tensor properties. Force is a first-rank tensor property, single hat, just like we talked about with moments as well. So it has basically a direction and has a magnitude as well. So we are going to actually see now how we are going to define stress and work with stress and strain in this tensorial definition. So previous definition here, also shear stresses. So we'll see that for shear stresses, we're going to see that we're going to define positive faces of the elements as those with the positive in the 1, 2, and 3 direction. And shear will act in the positive direction on positive faces or act in the negative direction of the negative faces. We'll describe that in just a second. Shear stress, this tau, you'll typically see that value, same units. We will not use this. We'll typically use our tensorial definition. But if you see tau, that is typically going to talk about engineering shear stress. Gratefully, thankfully, our tensorial definition of stress and or shear stress is going to be the exact same as our engineering definition, but unfortunately for tensorial shear and engineering shear, that is not the case, and that's going to cause some complications for us, unfortunately. So, again, stress, second-rank tensor property, first-rank tensor properties are vectors. We've seen those before. This is kind of what we were talking about previously for shear, but we'll kind of approach it in the context of essentially this tensor. What's the difference between a matrix and a tensor? A tensor indicates basically a coordinate system and directionality. Matrix is just a matrix of numbers. So we're going to define tensors like this or like this. And we're going to have two indices, I and j, because we have a second-rank tensor property. So when we define stress, we're going to describe a force in the j direction, and the a sub I is the normal to the plane on which it's acting. So our full or our most generic stress tensor will be this. So we can actually, this is complex. It has 9 independent components, that's 9 equations, but this is actually not the case. So we previously mentioned that our element, or our representative volume element, must be in equilibrium. So the sum of the forces and the sum of the moments must be equal to 0. That is going to allow us to drastically reduce the number of the elements in here. But before we get to that, let's just kind of describe and show 1, 2, and 3 what stresses may look like. So if I'm looking at the stress, for example, in the 3, 3 direction, the normal to this plane will be in the 3 direction. Agreed? Yes. If I pull in the 3 direction, this stress will be the stress in the 3, 3 direction. If let's delete this here. Oops. If I pulled like this, so J, the direction of the force in the 2 direction, and then the area, also in the 2 direction, it'd be this. All right. What if I do a stress like this? So when I'm looking here, what's the direction of this force? So it's pointing in the 2 direction. So it is pointing, my J is in the 2 direction. What's the normal here? 3. Sigma 3, 2. So that would exist right here. You can also see, again, this is what I was talking about, positive. This shear will be positive. So previously when I was pulling here, that sigma 2, 2 would be positive. If I'm pushing down here, then the value would be negative. But we know this is positive because we define the top face as a positive face, and it's pointing in the positive 2 direction. If it was pointing in the opposite direction here, and if this was pointing in the opposite direction as well, then we're going to define this. It's on the positive face. If it's pointing in the negative direction, that will be negative as well. But in the previous, and then here on the negative face, we're pointing in the positive direction. So we would define this as negative sigma 3,2 shear. So remember, on the positive face, it has to point in the positive direction. And then on the negative face, it has to point in the negative direction for that shear to be positive. So let's do one more. How about I draw this? Normal stresses are pretty straightforward. What if I do, let's do this. Actually, let's do this. What is this stress? So again, where's it pointing? Pointing in the 3 direction. What's the normal here? 2 directions, so sigma 2,3. Is this positive or negative? Again, this is my positive face. It's pointing the -3, so that's going to be a negative stress here. So that's how we kind of draw out, and again, that's how you define positive and negative shear as well. But let's get back to this example. We have to have static equilibrium, so the sum of the moments, the sum of the forces must be equal to 0. And right now we have 9 independent equations. I don't think that we need 9 independent ones. So let's look at this example here. So the sum of the forces in my 2 direction must be equal to 0. So again, in the 2 direction, I have, if I'm looking at the 2 direction here, I'm going to have a force, which is going to be sigma 3,2 right here. Again, positive here. Sigma 3,2 times the area, which is going to be sigma 1 times sigma 2, minus the sigma 3,2 that's pointing in this direction, for example, times sigma 1, 2, sigma 3,2. And so this equation has to hold. It's actually sigma 2, 3, but anyways, we can look at that. Again, trivial result. This is 2, 3, excuse me. But it must hold. So we can actually see, actually, sigma 3, 2, excuse me. So they must be equal in magnitude. But again, we could also pick a point, the moment around my 1 axis. So let's look at the moments around that 1 axis. So if I look, I see that I'm going to have, again, the force around this 1 axis, here and here, they're dead. Because basically they're touching that, they're around that moment. There's going to be 0 magnitude there. But if I look at my sigma 2,3, and then that is going to push me where? In the counterclockwise direction, so that's going to be positive. So sigma 2,3 times, again, force times a distance. And that distance, so if I look at the force on the 2,3, so my force is going to be equal to sigma 2,3 times, again, the area. So delta 1 times the area, delta 3. So as you can see here, this is my force times the distance from my 1 axis is going to be delta 2. So that's positive. If I look at here, this is going to send me clockwise. So again, force is going to be sigma 3,2 times sigma 1, sigma 2. What's the distance to my 1 axis from this force here? It's going to be that sigma delta 3. Excuse me. I'm going to mix up the delta there. So when I do this, I will find that these must be equal. And you can see here, these must be, I forget that equal as well. So you can extend this proof and see that these off-diagonal components must be equal. So we end up from 9 to 6 independent components, as you see here. So sigma 1, 2 is now equal to sigma 2, 1. Sigma 1, 3 is equal to sigma 3, 1. Sigma 2, 3 is equal to sigma 3, 2. So it's really nice. And again, this all comes about because of the static equilibrium condition. So now, the next time, we could do look at some examples of defining, essentially, stresses with all these different notations. We've already kind of touched on it a little bit, but we'll do some more examples next time. All right, thanks. See you next time.